Welcome back to the greenhouse of math. Yes, that's what we do here. I want to talk to you today about something maybe you've heard of, fractal. Have you ever heard of that word? Fractal? Sounds like fracture. It's not. It's fractal. It's a math word. It's a pattern word. There's fractals all over the place. One example, the shell. It's a pattern that repeats itself. And if you actually look really close, the spiral is coming out of the shell at a very predictable patterned amount. There's fractals all over. Let me grab another fractal here. There's a beautiful tomato plant. The veins on the leaf of the tomato plant produce a fractal. There's a large one, it splits. Those little ones split again. Eventually it ends, but there are some in math and some around the planet that almost seem to go forever. Okay, you'll see them in crystals. Maybe you've had a mirror where you have the two folding mirrors in the bathroom and you fold them in and you look into one and you can see that reflection go forever, infinitely behind you. That's a fractal. Okay, now fractals, they actually have a lot of value. They're beautiful to look at, which you can look at the next video where we make one. The art looks really nice, but they're good for solving problems because they're predictable and they help us predict what might happen in the future. Now, right now with this whole COVID thing, there's actually some people using fractal-like math to predict how many people might get infected as this thing goes on. Okay. Now you might have heard of the term the R0 value or R naught. It's basically the ratio or the amount of infected people that can infect more people, right? So if one person, let me show you here, and this is a fractal, if one person can infect two people, so we would say the R0 value would be 2, that one person is going to infect 2 new people. Okay. So this person here starts out, they are my patient 0, they're the first one. These next ones have undergone one stage of infection, and I'm going to call them my patient number 1s. Now if I go up the next step, keeping in mind that the R0 value is 2, each one person at this stage has to infect 2 people. Okay, this would be my patient number 2s. They become infected after 2 steps. 1, 2. Pretty cool, hey? Now, if we count up the number of people at each level of infection, or at each stage of this fractal, we'd have 1. We go up the next stage, we have 1, 2, 2. The next stage, we have 1, 2, 3, 4, 4. Do you remember what the R0 value was here? It was 2. So if I say 1 times 2, I'm going to get 2. Oh, that's my number at the next level. If I say 2 times 2, I'm going to get, there's my number of new infections at the next level. If I say 4 times 2, can you guess what I'm going to have at the next level? Well, remember, one person creates 2 new infections. One, 2, 3, 4, 5, 6, 7, 8. You guessed that. You're seeing a pattern. It's predictable. We can make it go on infinitely until we run out of whiteboard or paper. Or, well, you won't run out of numbers. You could do that forever in your mind. Try it. But what I want you to do is, based on this predictable factoring, patterning math concept, fractal, I want you to change up the R0 value. Could you imagine if this first person didn't infect 2, but the R0 value was 4? So what if it was like that? Squeeze one more person in there. That first person has infected 4. 1, 2, 3, 4. I'm going to change those because I'm going to end up having more cases, more infected people at each level going up. So what I want you to do is use this concept of math and this fractal pattern, this predictable pattern, to make a prediction. If you had a virus or a bacteria, an infection, that had an R0 value of 3, and one that had 4, and one that had 5, so you're going to have to do 3 different images, right? What would the total number of new cases be once they hit the 5th round of infections? So this is math that allows us to get a bit of a ballpark for what numbers might be. Now, of course, it forgets that this person will reinfect again at this level and so forth. But it gives us a bit of a ballpark idea what's happening. Okay, so I want you to draw out, or you could use pieces of paper, or you could use jelly beans to lay it out, but draw out a fractal for 3 different make-believe infections that have R0 or R0 values of 3, 4, and 5. Let me start you out with the one that has a 3, just so we're clear here. There is my patient 0. Okay, no infections have happened yet, but they're the first infected. They're going to infect 3 this time, remember? 1, 2, 3. All those people are my patient number 1s. They've got new infections after 1 round of infection. And now I'm going to go up the next one. Remember, each one of those people need to infect 3. This is an R0 value of 3. Draw one of those up. Once you go 1 stage, 2, 3, 4, 5. Tell me how many you get across the top. Okay, and you're going to tell me that for an R0 value of diseases or infections that have 3, 4, and 5. See if there's any big difference. I mean, these numbers here, they're right beside each other in the number line. I mean, how big can the difference be? Give it a try. And a bonus question for you keeners. Describe to me how this fractal type math, this predictable patterning, relates and compares to what you know about exponents. Okay, we've studied exponents already. You guys are pros. Remember, you have a base and you have an exponent, right? Maybe you're going to write it like, oh, that looks familiar. You could even write it with just letters. Your base, there's your exponent. Tell me how this math, exponent math, relates to fractal math. That's it. Go to it. Send me a picture of your cool fractals. Send me some numbers. Go. Do it.